Hello everyone, my name is Leo. Today I'm going to present Solythesis, a source-to-source compiler that enables runtime validation for smart contracts. This is a joint work with Andrew and my advisor Fan. Ethereum is a blockchain platform which allows users to create and interact with smart contracts. A smart contract defines sophisticated transaction rules and further be executed and guaranteed by the Ethereum blockchain system automatically. They are widely used to implement digital assets and decentralized applications. Once a smart contract is deployed, the transaction rules cannot be modified. However, programmers make mistakes, and mistakes lead to bugs and errors. Errors inside smart contracts are particularly severe since it is treated as intended transaction rules and enforced by the consensus algorithm. Millions of dollars lost forever due to bugs and errors in smart contracts. Static analysis has been widely adopted to find bugs and errors for traditional software because it introduces zero runtime overhead. It is natural for researchers and developers to use static analysis to detect bugs and errors for smart contracts. But static approaches may report false negatives, false positives, or even never return a result. On the other hand, the overhead worried by most people is not a problem for smart contracts, because the execution environment of the blockchain system is totally different from traditional software. This picture shows the architecture of the current Ethereum blockchain system, which is divided into three layers: the consensus protocol layer, the storage layer, and the transaction execution layer. As you can see, transaction execution is only a small part of the entire blockchain architecture stack. Our hypothesis is that the performance of the entire blockchain system is dominated by the storage layer and the consensus protocol layer. In order to understand the real bottleneck of the current Ethereum blockchain system, we execute smart contract transactions using parity, which is the fastest Ethereum client under 2 configuration, with consensus enabled and with consensus disabled. Our observation shows that the consensus algorithm is the main bottleneck of the current Ethereum blockchain system. As you can see that parity can only process 9 to 34 transactions when the consensus algorithm is enabled. This is because Ethereum generates blocks every 15 seconds and it can only process certain amount of transactions in each block. Therefore, given the current execution environment of smart contract, our hypothesis is that the overhead of the runtime validation can be negligible for smart contracts. But does smart contract execution influence the performance of the Ethereum blockchain system at all? The answer is yes. The overhead of runtime validation can be negligible if and only if we do it properly. We'll analyze the performance of the parity client to understand the second bottleneck, when consensus is disabled. Our result shows that over 68% of performance counters are related to state load and store operations. Other EVM parts only take 9%. Since the smart contract is bottlenecked by I/O, reducing the storage operations should be the highest priority for compilers and runtime validation tools. This implies our design decision. Runtime validation tools of smart contracts should minimize the number of instrumented load and store statements that access blockchain state. Next, I'm going to present our work, Solythesis, which is a source-to-source compiler guided by previous observations. Solythesis instruments Solidity smart contract source code and enforces standard invariants dynamically. The instrumented smart contract will reject transactions if it violates invariants. It also minimizes the storage accesses so that the transactions can be executed efficiently. Here is an example. ERC-1202 is a standard for smart contracts to implement voting. It supports hosting multiple issues, and for each issue, it contains multiple options to vote. Each participant may have a different weight on each issue, and the option with the highest accumulated weight wins. This is a simplified code of the ERC-1202 example, provided by the standard proposer. The contract uses 3 state variables. Weights store the weight of each participant on each issue. Weighted vote counts store the total weighted count of each option on each issue. Ballot stores the vote of each voter on each issue. Consider Alice, Bob, and Ming are planning to use the vote contract to decide what to eat today. Alice and Bob want to eat burger, and Ming wants to eat pizza. First, they initialize the vote contract and use 0 as the issue ID. They set the weight of each participant to 1. Set their ballot to empty. And for each option, burger and pizza, the initial weighted vote count is 0, since no one has voted that option yet. The contract defines a vote function, which allows a participant to vote an option of an issue. It first fetches the weight of the transaction initiator. Then, it updates the weighted votes of the given option on the issue, and stores the current vote to ballot. Alice, Bob, and Ming call the vote function with their desired option separately. However, there is an implementation error in the contract, which allows the user to vote multiple times. Here, if Ming calls the vote function 4 times, the weighted vote count of pizza will be set to 4 instead of 1. It breaks an implicit invariant among those 3 state variables. The total weighted count of an option on an issue should equal to the sum of all weights of voters who voted for the option. An easy fix could be adding the green line in the code, which first updates the weighted vote count of the participant's previous voted option. You may think that such error is rare in production code. Ironically, this is the example implementation provided by the standard proposer. The bug will be exploited if someone deploys this smart contract without any modification. We next apply Solythesis to the contract and describe how Solythesis instruments the contract to nullify these errors. First, let's define the invariant of the ERC-1202 standard. The first line defines an intermediate map S that corresponds to the sum of all weights of the voter that voted for issue and option pairs. The free variable A iterates over issues, B iterates over voters, C iterates over options of an issue. For each map entry as a C, it iterates over all voters to sum the weights of those voters who voted for the option C on the issue A. The second line defines a constraint with a for quantifier to specify that for all pairs of issue and options, the intermediate map S should equal to the calculated weighted vote counts in the state. This example shows that our specification language is powerful enough to specify sophisticated invariant. To implement this, a naive approach could be using 2 loops. The first loop iterates over all issues and all accounts to compute the intermediate variable S, which adds the weight of the voter B on issue A to his or her ballot. The second loop iterates over all issues and all options to assert that the total weighted count of an option on an issue should equal to the sum of all weights of voters who voted for the option. The naive approach will cause prohibitive overhead because of the iterative sum operation and the quantifier constraint. But do we need to recompute and check all values in S? The answer is no. We only need to update and check the value in S where X equals to issue ID and Y equals to the sender's previous and the new ballot. Therefore, Solythesis implements a delta update technique to update all intermediate variables. For every write operation to an original state variable in the contract, Solythesis performs static analysis to determine whether modifying the original variable may cause the intermediate value to change. It then runs binding algorithm to bind free variables defined in the invariant to smart contract expressions based on the semantic of the expression and invariants. To learn how we did this, please refer to our paper. In this example, Solythesis detects that the assignment expression may change the intermediate value of the sum expression. It then binds a free variable A in the invariant to issue ID, binds B to message sender, and binds C to ballot of issue ID of message sender. These bindings indicate that the write to ballot of issue ID of message sender may only change the intermediate value of SAC, where A equals to issue ID and C equals to ballot of issue ID of message sender. Then, Solythesis instruments the smart contract based on the semantic of the sum expression. It first subtracts the weight of the transaction initiator from the transaction initiator's previous vote. It then adds the weight to his or her current vote. For every state write operation, Solythesis also checks it against the assert constraints in the invariant. In order to do this efficiently, Solythesis only checks relevant instances of X and Y when S is updated or weighted fault count is updated. For the write operation to weighted fault counts, Solythesis first runs its binding analysis against the constraint which contains a for all quantifier. This analysis determines that the write operation may cause the contract to violate the constraint when X binds to issue ID and Y binds to option. Solythesis defines additional arrays like X array and Y array to collect such free variable combinations that may lead to constraint violations. It then instruments statements to maintain these arrays. Same as weighted vote counts, Solythesis also determines that the write operation of state variable S may cause the contract to violate the for all invariant. It instruments the contract accordingly. Solythesis finally instruments a loop at the end of the transactions to only check these potentially violated constraints. With these instrumentations, the latter transactions initiated by min are rejected because they break the invariant. Besides delta check, Solythesis also implements other optimizations to minimize storage access. We next evaluate Solythesis on three representative standards: ERC20 for the fungible token standard, ERC721 for the non-fungible token standard, and ERC1202 for the voting standard. The goal of this evaluation is to measure the overhead introduced by runtime validation and to understand the effectiveness of the Solythesis instrumentation optimizations. When the consensus algorithm is enabled, our results show that for all contracts, the transaction execution consumes only a very small portion of the CPU and disk resources. We observe that the CPU and disk usage of Solythesis instrumented contract is low, and the delta between Solythesis and original benchmark is negligible. On the other hand, our results show that the CPU and disk overhead introduced by the baseline instrumentation is significant. the overhead introduced by Solythesis is negligible, considering the current capacity of CPU and disk storage and the cost of solving proof of work. The results validate our previous observation that the transaction execution is not the bottleneck of the Ethereum blockchain system. For ERC-721 and ERC-1202, we got similar results. Since there are ongoing research working on improving the performance of the current blockchain system, we would like to understand how Solythesis performs when the consensus is no longer the bottleneck. Even in the worst scenario, where the consensus algorithm is no longer the bottleneck of the blockchain system, our results shows that the instrumentation overhead of Solythesis would still be acceptable. Parity is able to process 556 to 2,211 Solythesis instrumented transactions per second, which is a long way for consensus algorithm to reach. Runtime validation is an effective and efficient approach to secure smart contracts. In this work, we propose Solythesis. With the delta update and delta check techniques, Solythesis can efficiently enforce powerful invariants with quantifiers for the state of a smart contract. Solythesis is an initial step in this direction, and we believe that new languages, new analysis, and new virtual machine designs that can further exploit rigorous runtime validation are promising future directions to secure smart contracts. Thank you for listening to my talk.